If you're using semicircles, it'd be 1/2 pi r squared. If you're using triangles, it's going to be a little bit different. It depends on what type of triangle you're using there, but more or less base times height, although you got to get it in terms of one variable there. If your cross sections are perpendicular to the x-axis, then it's going to be in terms of x. If your cross sections are perpendicular to the y-axis, it's going to be in terms of y here. So let's just do a problem so we can get an idea of what this looks like. You do not necessarily need to write every word of that, but you, of course, you want first quadrant, you want your equation and the axes, and then volume of the solid formed by constructing square cross sections perpendicular to the x-axis. Okay, so with all of these, it's a good idea to sort of graph what you're dealing with here. So we only want the first quadrant, and we just need, it's 1 minus x squared, so we're really just going to have this one little piece right here. Here's 1, and it'll look like this. But we only need this part here. So our cross sections are perpendicular to the x-axis. So that means, like, at each point, if we were like actually building this, we would, like, if you're thinking of this birdhouse here, we would take cut out a base that looks like that thing there. And then what we would do is we would measure perpendicular to the x-axis. So we would measure like how far across it is right here. And then we would cut us out a little square there that's got that same height as whatever we measured. And then we'd go to the next cross section here, and we'd make another square and another square until eventually, that's definitely not square, that last one, but until eventually you had this sort of shape. It'd start with little squares down here, and then it'd get bigger to this side, right? So you can kind of try to visualize what that would look like. It makes really cool shapes whenever you do this stuff, if you could like actually see it. So whenever we are finding the volume of this, we're going to use the formula for the area of the cross section. So area of a square is what? It's base times height, but in a square, base and height are the same, so you could just call it side squared. Here. Okay, so if we're using square cross sections, we will not have a pi. Okay, the pi comes from rotating whenever we rotate, and when we rotate, we end up with, when we rotate, each one of those little cross sections there is a circle because you've rotated it to get that point, and that's where you get the pi from. For these, you will not have a pi in your answer unless your cross sections are semicircles, because obviously the area for a semicircle is going to have a pi in it. But if you have a square, rectangle, triangle, any of that stuff, you are not going to have a pi in your problem for these. So if you look, the length of one of the sides of these squares when you're making those cross sections, that is the distance from 0 up to the equation, right? So that side, in this case, just equals 1 minus x squared. So what we're going to do is we're going to integrate. We will integrate from 0 to 1. We're using the limits from our x-axis here. And then our area formula is side squared. So our side is 1 minus x squared dx. There's no pi because we're not rotating here. And the only reason we even have a square is because that is part of the formula for the area of a square. It doesn't have anything to do with like pi r squared like the other problems. So you will not have pi in your answer unless you're using semicircle cross sections for this. So this is the area, this side squared is the area, and then when you integrate from 0 to 1, that makes it volume because that sort of finds the area of all these squares all added up from 0 to 1. Yes. And you'll have like a big square on the side, and then a little bit smaller one, a little bit smaller one, and then they'll all be lined. You'll have a solid edge on this side that'll sort of go down, but over here it'll sort of come in this way. If you can kind of picture what you're looking at, sometimes it's hard to think of it 3D. So what we're doing is we're taking the area of that square, which is just the equation squared, and then we're adding all of those squares up from 0 to 1. If we could make them infinitely thin. If you think of Riemann sums, we could actually make rectangles like that birdhouse over there. We could measure how wide each piece of plywood is, and we could find the area of each one, or the area volume of each one of those, and add them together. And then if we used thinner plywood and had more, it'd be closer to being perfect. But integrating gets it exactly as if it's smooth there. So here to integrate this is not too bad. We've got 1 minus 2x squared plus x to the 4th if we multiply that out. And then so when we integrate, we don't need the integral symbol anymore. When we integrate, we'll have x minus 2/3 x squared plus 1/5 x to the 5th, and that is from 0 to 1. So we'll get 1 minus 2/3 plus 1/5. So 15 over 15 minus 10 over 15 plus 3 over 15 is going to give us 8 over 15, and that would be units cubed. I should have looked some pictures up ahead of time. I need to add them to these notes. But there's some buildings and stuff that are built, really cool buildings, museums or something fancy. That buildings that are built with this sort of thing in mind. You've got it's sort of built in this manner, which makes really neat looking buildings there. I'll look up some of the pictures and show you guys on Monday, but I didn't do that yesterday. Here is our second one we're going to look at today. And we're just going to look at these first two today, and we'll finish them up on Monday. So your key things to write down here, the curves here and cross sections are perpendicular, or let's see, parallel to the y-axis and semicircular discs. Now, notice what they gave you here. They worded it differently, but it says parallel to the y-axis. Does that mean this is in terms of y? It does not, because if it were in terms of y, it'd be perpendicular to the y-axis. So parallel to the y-axis is the same as perpendicular to the x-axis. So sometimes it is worded that way, and as we do a lot of these, it's going to be kind of tricky because you probably, usually it says perpendicular, but sometimes it'll say parallel. So this one is still going to be in terms of x. Let's get a quick graph of what we're looking at here. So I think it will be first and second quadrant is where this is going to end up. We'll have 1, 2, 2. So for our x squared, we'll graph that in blue. We'll have here. And then I'm going to graph 2 minus x squared in red. That will be the graph upside down. Yes. So you'll have these like 2 intersecting parabolas here. Mine probably looks more circular than it actually would be. It would be a little bit different. In fact, Jarrett's butterfly up there may have been 2 parabolas intersecting like that, but just he used really skinny parabolas for that. And so this area right here is our base. If we were actually building this, we'd cut out a shape that looked like that. We might do a project. I'm thinking of such good projects. Because look, if you look at this eraser right here, I feel like it, with that exception of the way it's kind of like caved in right there, like you've got this base, you got these curves. I feel like this is cross sections right here. If you slice each one, it's a weird cross section. It's like a square with a semicircle on top, sorta. But it's pretty much the same with the exception of the cutouts there. We might do like a reverse engineering project where you've got to bring in something that you could make with equations. We might do it. It'll be easier than doing that project because you won't actually have to make it. You'll just have to make the equations to make a figure. And then if we could like make it show up on the computer, that would be so cool, but I don't think we have software that'll do that. But, so, we might have to do it there. Alright, so our semicircles this time, we'll take like a slice here, and we'll be building a little tiny semicircle right there. And then we'll move over to the next part, and then we'll build a semicircle here, and then we'll have our next one. Will be bigger. That's not a very good semicircle. And then your tallest semicircle is going to be right there in the middle, and then they'll get smaller again on the other end. So that is what we're looking at. Semicircles are they're a lot harder than the squares because there's a couple things to remember. Whenever we're looking for area for the semicircle, the area for the semicircle is going to be 1/2 pi r squared. One of the most tricky things about this is that you're not using the diameter of the circle, but the radius of the circle. So, like, whenever we're looking at our cross section here, right, that is our diameter of the circle. So, before we can put it into our equation, we have to cut it in half. So, if we look at this, like the diameter of our circle, that's going to be top equation minus the bottom equation, right? So the diameter of this circle would be 2 minus x squared minus x squared. Which if you want to simplify there, the diameter is 2 minus 2x squared. But for a square, we would use that diameter. We would use that because we take the length of the side and just square it. So we'd have 2 minus 2x squared. But for a semicircle, we don't use the diameter, we use the radius. So the radius would be 2 minus 2x squared divided by 2, which is going to give us 1 minus x squared here. Okay, so you got to think, most of the time you're just using that length there, which is top equation minus bottom equation, except for semicircles because you have to have a radius instead of a diameter. So for this problem, we're going to have to integrate, and we will integrate from -1 to 1. And just like with the volume problems, it's probably not a good idea, although this is symmetric and it seems like it should work, it's probably not a good idea to cut it in half. I think sometimes it works, but I think sometimes it doesn't, and I'm not great at knowing when it does and doesn't, so let's just do this way. So from -1 to 1, we would have 1/2 pi times 1 minus x squared squared. Yes. Okay, and then, so what I would do is I would take this 1/2 pi, it's just a coefficient, I'd put it out front because that just makes it easier to integrate. So you'll have pi over 2, integral from -1 to 1 of, I'm going to go ahead and multiply this out, 1 minus 2x squared plus x to the 4th dx. And then so we are going to integrate here. We're just going to leave our pi over 2 out front. So we'll get x minus 2/3 x to the 3rd plus 1/5 x to the 5th. And we're evaluating that from -1 to 1. I think I'll do this by hand. If it gets much worse than this on your homework, just use the calculator for it, but let's try this by hand. So 1 minus 2/3 plus 1/5, whenever we plug in our 1, minus -1, it's going to be plus 2/3 minus 1/5, because whenever you have that -1 to the 3rd or to the 5th power, it's still there. And so if we distribute this negative, that makes this positive, that makes this negative, and this positive. So we have pi over 2, we'll have 2 minus 4/3 plus 2/5. So 30 over 15 minus 20 over 15 plus 6 over 15. So we get pi over 2 times 16 over 15. So we end up with 8 pi over 15. Right, does this little reduce here? Yeah, 8 pi over 15. And that is units cubed. Okay, questions? Alright, we got a few minutes. I'm just going to assign just a few for homework here. Our book really doesn't have a lot of these. I'm going to have to sort of supplement on some of these. Okay, we are going to do page 428. I want you guys to do 70 A and D and 71 A and C. I do need to tell you one thing about 71. 71 gives you the equation like this. For 71, it gives you x squared plus y squared equals 4. What is that the equation of? Circle, right. To be able to do the problem, you're going to have to solve it for y. So you would subtract the x squared, and so you would have y squared equals 4 minus x squared. And you would square root both sides, which would give you y equals plus or minus the square root of 4 minus x squared. And so let's think about what that looks like a little bit. Like, you know that this is a circle with a radius of 2. And so whenever you're doing this, y equals positive square root of 4 minus x squared is the top half of the circle. And then y equals negative square root of 4 minus x squared is the bottom half of the circle. So you can use those two equations as your top and bottom equation whenever you're doing the problem. For that, they give it to you without splitting it up. But once you have it like this, then it's just like the other problems.